Well, good afternoon. It's 12:21 on a Monday afternoon, the 5th of November. It's supposed to be Calculus 3 class, and right now I'm the only one in the room again. A little late getting here, but I was trying to wrap up something before I got here, but looks like no rush. Anyway, here we are. Let's start with the current slide. Let's see, are there anything special I need to announce to you? Number one, of course, tomorrow's election day. I hope everybody's planning to vote. And then sort of a bad news situation. Good news, bad news, I guess. Next Monday is Veterans Day, which is a state holiday. That's sort of the good news, but the bad news is that means we'll miss class. So we got class today and Wednesday, and then won't meet again until the following Wednesday. So try to get over that. All right. Trying to think if there's anything else that needs to be said. I have, just on a personal note, finally almost completely finished the spring schedule. I did think of one other thing over the weekend I probably need to adjust, so I'm going to try to do that this afternoon. But then after that, I think I'm through with spring schedule, so I'm going to be grading papers like crazy. And at that point, hopefully I'll get some of your work graded. And then at some point, get them on Blackboard, because I've got just tons of grades to do. And I've got 4 hours a day. I hope to spend most of that 4 hours grading papers, though I've got a little bit of other stuff to do. And then I've got 4 hours tomorrow. It's really never 4 hours because I have to eat, sometime in there, but close to it. And I'll try to get more graded then. Hopefully I'll have most of it graded by Wednesday, but no promises. All right, with that in mind, where we left off last time was in Chapter 13, Functions of Several Variables, 13.8, Directional Derivatives and Gradients. And that's where we are. Now, there's example 3s given here, and that's where we left off last time. We had talked about what a gradient was, and now let's actually find one. So find the gradient of f of xy is equal to y log x, natural log of x, plus x y squared at the point 1, 2, the gradient at that point. Okay? Now, in case you've forgotten over the weekend, here's what the gradient is. That symbol is called a del, also sometimes called grad. Del f is the partial of f with respect to x in the I direction, partial of y, f with respect to y in the j direction. So it's the del, the gradient is a vector. The function's a scalar function, and when you do the gradient of it, you get a vector quantity out of that. So what we'll need to know here, let me get my pen set up, what we'll need to know is f sub x of xy, and in this case, hold the y constant, and the derivative of log x is 1 over x, so this is y over x is your f sub x. Your f sub y, oh, I'm sorry, that's not all of it. That was the first term, plus partial of f with respect to x of the second term is just y squared. Okay? Your f sub y at xy would just be log x, because the partial of the first term with respect to y is just log x plus 2xy. Okay? So what is the gradient of f at that point? The gradient, and I'll put an arrow over it to remind myself it is a vector of f of xy, is equal to the partial with respect to x times I, so that'd be y over x plus y squared I plus log x plus 2xy j. This is a two-dimensional vector, so that's a plane vector in the plane. All right, we need it at the point 1, 2. And you really don't need to know it, but when x is equal to 1, log x is 0, so the first term is 0, and the second term would be 1 times 4, that would be 4. So when at the point 1, 2, the functional value is 4. Not that you really need to know that at this point, but yeah. So what's the gradient at that point? Del F at 1, 2 would then be 1/2, no, I'm sorry, 2 over 1. Yeah. 2 plus 4I plus log of 1 is 0. 2 times 2 is 4j. Okay, so that would be 6I plus 4j. All right. That's the grad 6I plus 4j. Grad or gradient of f at the point 1, 2. First takes the partials at xy. Don't plug in to begin with, or else you probably are going to wind up with zeros, you know. So take the partials with respect to the variables first. Then once you've done that, plug in the values. Okay? So that's how we did it. Let's see if they did it any differently. I can't think of many other ways you could have done it. Let's see if they came up with any clever ideas. So we first did partial of f with respect to x at xy, which is y over x plus y squared, exactly what we got. And partial of f with respect to y at xy is log x plus 2xy, exactly what we have. And then they did the same thing we did. You wrote down what del f is. The gradient of f, any value xy, is your partial of f with respect to x at xy in the I direction plus the partial of f with respect to y in the j direction. And when you do that, you get x over y plus y squared I plus log x plus 2xyj. Plugging in the values at point 1, 2, the gradient is 2 plus 4I plus 4j. So that's 6I plus 4j. Done. Okay. Now, that's what a gradient is, how you get a gradient, but what is it? Because the gradient f is a vector, you can write the directional derivative of f in the direction of u as, and the symbol there is d sub u, directional derivative of the function f in the direction of u. Now, u doesn't have to be a unit vector. Quite often it is, but it doesn't have to be in any direction of a vector u. As the partial of f with respect to xyi plus the partial of f with respect to y at xyj, and dot product that with cosine theta I plus sine theta j. Okay? Now, in other words, the directional derivative is the dot product of the gradient and the direction derivative, the derivative that you are trying to put in that direction. Okay, now, they just came up with the thetas up here. You would have to have something to tell you what that theta was. So the alternative form of directional derivative, if f is a differentiable function of x and y, has to be that. The directional derivative of f in the direction of the unit vector, and this time they specify it is a unit vector u, is directional derivative in direction u of fy is the dot product of the gradient of f with the unit vector u. Okay. Now, again, absolutely right, cosine theta I plus sine theta j is u, but you need to know what theta is. So that form is not a very useful form unless you have some relationship between theta, and generally going to be a trig relationship, and the components of u. Okay? So here's example 4. Okay. Find the directional derivative of this function f of xy, 3x squared minus 2y squared at negative 3, 0 in the direction from p, which is negative 3/4, 0 to q, which is 0, 1. Okay, so several places that you could begin. It really doesn't matter how you start this problem. At some point, you're going to need to know the partial of f with respect to x at xy, and that's going to be 6x. Partial of f with respect to y at the same xy value would be minus 4y. Okay? Simple partial derivatives. Okay. All right. I'm trying to think now. There's a real temptation to go and plug in the values. I see no reason not to. The one thing just wanted to check something here. When you did plug in that value, that would be 9/16. Okay, I was trying to determine here if indeed that point, that function is defined everywhere, so it certainly would be defined at negative 3, 0, negative 3/4, 0. So negative 3/4, 0, its value, though I don't think you need to know this, that would be 9/16, 27/16. Yeah, you don't need to know that, I don't believe. But in the direction from P to Q, so you need to get the vector that goes from P to Q. So let's name it that way, PQ. This would be, I like vector notation, 1 3/4. Because you do. No, I did them backwards. Sorry, goodness gracious, where's my brain today? 3/4, 1. Okay. From P to Q would be 0 minus a minus 3/4, which is 3/4, and then a 1 minus 0, which is 1. Okay, so there's the vector. Now that obviously is not a unit vector. Okay, the question is, does it matter? Yes, I think it does. So then we need to get the unit vector in that direction. And that would be this thing, 3/4, 1, divided by the magnitude of 3/4, 1, which would be the square root of 9/16 plus wait a minute. Yeah. And that would be 16/16 plus 9/16 25/16, so that would be 5/4. So it would be 4/5 times each of that. So that would be 3/5, 4/5. Okay? That's the vector. It's a unit vector in the same direction as 3/4 as the point from P to Q, vector from 3 to P to Q, but it's the unit vector in that direction. All right, so yeah, what I was thinking before does work. Your gradient of f, let's just write it as xy to begin with, is equal to 6xi minus 4yj, and at the point -3/4, 0, that gradient is -9/2 I, -9/2 I, because the y value is 0, so minus 4y is 0. Okay? So there's the gradient for f at that point, and then you dot that with 3/5, 4/5, and that would simply be, goodness gracious, 27 minus 27/10. Okay, that's the directional derivative at that point. Okay, that's how the function is changing in the direction of that vector there. It's going downhill at almost a 3-to-1 rate, but that's exactly what we've got here. Okay. All right. And then they do show a picture in the book that I'm not about to reproduce, but let's see if they do show it to us. I think we have a student coming. Nope. Hey. For just a second. I had a student come in. I was hoping it might be one of us, but it wasn't. So let's get this cleared and see how they proceed with the problem. Because the partials of f are continuous, f is differentiable, you can apply theorem 310. I forgot to even look at that, but it certainly does work. A vector in the specified direction, P to Q, would be what we said, 3/4 I plus j. I wrote it as in vector notation, 3/4 1, same deal, okay? The unit vector in that direction is, you got to divide by the magnitude. The magnitude is 5. Make sure that is true. Yeah, that's what we determined. Well, unit vector will be 3/5 I plus 4/5 j. All right, because the partial of f with respect to the del f is the partial of f with respect to x, I plus partial of f with respect to yj, that's 6xi minus 4yj. The gradient at that point is, this is the gradient now, at 3/4 0, -3/4 0, is simply -9/2 I plus 0j. Okay? So there's the grad f. I think that's the same thing we had. Can't remember now, but it seems like it was. Consequently, at the point negative 3/4 0, the directional derivative would then be the dot product of the gradient with the unit vector we just determined, and that would be negative 9/2 I plus 0j dotted with 3/5 I plus 3/4 j, which is merely negative 27/10 plus 0. Okay? And there's the the graph of this function. And I don't know if you recognize it or not. I probably should have mentioned that it was a hyperbolic paraboloid. And okay, can't think of anything else. It's just really hard to see. The point down there, minus 3/4 is P. Okay. The value of the function there is up here. Okay. P to Q would be P to the point, what was it, 1, 0? Yeah, 1, 0. That would be the direction of that vector. Okay. And when you dot that with the gradient here, you get the light blue line. You can hardly see it there because it's sort of in the crease, but that's a light blue line that's in the same direction as PQ. And sorry, that has a pretty significant negative slope there, negative 27/10, almost 3 to 1, negative 3 to 1 slope. Okay, so that's the directional derivative up at that point there on the curve, point corresponding to negative 3/4 0. Okay, so you see, if you were really graphing, you would have needed to know the z value of that. I sort of did it for you, but said we really don't need it. But if you're graphing, that would have been handy to have. So that was example 4. Now we move to, on page 924, applications of the gradient. Okay? Certainly to find directional derivatives would be 1. Here's some others. The first, properties of the gradient. Theorem 1311. If f is differentiable at the point xy, now what that means is both partials exist and make sense, are continuous and smooth, that kind of stuff. Okay? Now, if the gradient of f at that some point xy is 0, then the directional derivative in the direction of any unit vector u at f of xy is 0 for all u, for all unit vectors u. Okay. The direction of the maximum increase of f is given by del f at xy, and the maximum value of directional derivative getting all clogged up again. I don't know why. The direction of maximum increase of f is given by the gradient at xy. The maximum value of the directional derivative of f of xy is the magnitude of that gradient. Okay? That is the maximum value of the directional derivative of f of xy. Okay? Because the direction of maximum increase is the gradient, and so the maximum value there would be the magnitude of the gradient. Okay? Now the direction of minimum increase is then minus del f. So the del F always points to the maximum increase, and the opposite direction would then be the minimum increase. Okay, minimum value of the directional derivative of f of xy in the direction of the unit vector u is minus absolute value of f of xy. Okay. All right. So here's example 5. All right. There was a proof of that theorem on page 924 as well, but let's move on to example 5. Before we do, I hate to pause like this. It seems like I do it just about every day. But I've got to go get some water or something to clear my throat, so I'll be back. Okay, sorry about the delay there. I had to go get something to clear my throat, and it's not much better, but it's a little bit. All right, here's an example 5. This is on page 925 in your text. The temperature in degrees Celsius on the surface of a metal plate is given by this formula. T of xy, where xy are your grids of the plate, is 20, which would be, Celsius would be right around room temperature, minus 4x squared minus y squared. So obviously the temperature from the center, where x and y would be 0, would be at room temperature, and then from there on out is decreasing in every direction because x squared and y squared are both positive numbers, so you'd be subtracting something from that, where x and y are measured in centimeters. In what direction from the point to -3 does the temperature increase most rapidly? Okay. Well, where does the temperature increase most rapidly? In the direction of the gradient. Okay, so what we do is take the gradient of this function t of xy. Okay, I don't need that first parentheses. I don't think they usually put one in there. The gradient, of t of xy. Sorry. Throat still isn't back to normal, but it's good. Let's see what that is. That would be partial of f with respect to x. That'd be minus 8x in the I direction, minus 2y in the j direction. Okay? Partial of f with respect to x in the I direction, partial of f or t with respect to y in the j direction. So there would be the gradient, okay? So what would be the direction from the point to -3, where it would increase most rapidly? That would be, guessing toward 0, 0, but let's see. The gradient of the temperature at to -3 would be minus 16i plus 6j. Okay? Now, from the point 2, x equal 2, you'd be moving in the direction of minus 16i, and from the point -3, you'd be going in a plus 6j. That seems like that would probably make the most sense. Again, you're going, in a sense, toward the origin from the point where you were. Okay? Not exactly, but going somewhat toward it. Okay, so yeah, that's what they got in the text. Okay, so that's the first question. What direction from 2, -3 does the temperature increase most rapidly? What is the rate of increase? Okay. I think that would be the directional derivative. No, I'm sorry. That's what we were just talking about before. The direction of maximum increase is the maximum value of that would be the directional derivative. I'm right. Okay. So, so it would be the rate of increase is the term rate of increase doesn't jive too well with what they were saying before. They said the direction of maximum increase and the maximum value of that is the directional derivative. Of directional derivative there would be just the magnitude of the gradient. Okay? And then this to be saying the rate of increase, that this is how you get it. Again, there's nothing intuitively obvious that says that is the rate. What they say here, the maximum value of the directional derivative, which I guess is a rate. A derivative is a rate. So yeah, so I guess that would be it. So that would be the magnitude of -16i plus 6j. Just to write it down, that would be the square root of 16 squared. Is that 256? I don't have a calculator on me. Yeah, 256 plus 36, and that would be the square root of 290, whatever that is. Okay? Oops, 292. Yeah, I can't add. 292. Just adding my first two digits. Square root of 292, and then in the text they say that's about 17.09 degrees per centimeter. 17.09 degrees per centimeter. Okay, per increment in the direction of that gradient. Okay. Now, it's pretty high, considering that the maximum temperature it can ever be is 20 degrees Celsius, and this is increasing at 17.09 degrees per centimeter. It's not too far beyond this that you're going to be in fact, you might already be in negative temperature range. Let's just see. The indication would be that you would, but let's see what your temperature here is at 2, -3. It'd be 20 minus 16 minus 9. So yeah, you're already at negative temperature. It's -5 degrees Celsius here, and that's going to be increasing at a rate of a little over 17 degrees per centimeter as you go back in the general direction toward the origin. Okay. Solution presented here can be misleading. Although the gradient points in the direction of maximum temperature increase, it does not necessarily point toward the hottest spot on the plate. as I said, it's just in the general direction. In other words, the gradient provides a local solution for finding an increase relative to the temperature at the point. Once you leave that position, the direction of maximum increase may change. I would say it, not in every circumstance, but many it will change. Okay. So that's example 5. Let's see how they did it. Excuse me. First, they found the gradient, just like we did, minus 8xi minus 2yj. Okay? Follows that the direction of maximum increase is given by the gradient of that function, which when you plug in those values, you get minus 16i plus 6j. Okay? Now, you know the hottest spot here is the origin. That's at 20 degrees. Here your maximum increase is in this direction, but you know when you leave that, it's going to have to at some point swing around to go towards 0. It's good to see you. I'm so tired of talking to myself. All right, let me flip. Made these announcements at the beginning of class, but nobody was in here, so it'll be a while if you do listen to the YouTube video before you be able to hear it, because it'll be a while before it gets uploaded. So let me go and tell you now. Knock on wood, but I think I'm through with spring schedule. Oh, that has been such a big pain. I did think of a couple things over the weekend that I do need to change. Just minor little things, and if I can remember to do that this afternoon, knock on wood again, I hope it won't take me more than 5 minutes, because it's just a couple of minor things to take care of. But the way that schedule is, you do something little to it, it could cascade and become quite a bit worse. But anyway, I'm going to try to do that. Which, on the other hand, means I'm finally able to start grading some of all this huge stack of papers I have here. I picked up in the second mini-term a very large physical science class, and we have a lab every day, so that's 2 a week, and I've had, I think, 2 tests so far, so, I mean, it's lots of papers every day, so I've got a lot of that grading, in fact, just about all that grading. I barely got started on the surface of the first lab. So I've got all that to do, but I did get the first class this morning, which is another really large class. I got all of its grading caught up this morning. Of course, I've had a couple more things turned in today. So I'm mostly caught up on that one. I've got one other really big class, but I have most of those papers done already, because I was able to get them done last week, you know, in between times when I had little bits of time here and there. So if you've turned in anything recently, hopefully I'll get to it. I've got to get through that huge stack of labs and tests, but once I get through that, I'll have some time to work on this class. And that will hopefully, we'll be able to get caught up on some of that. Nothing's been put on Blackboard in quite a while, so as soon as I get the grading done, then I'll be loading on Blackboard like crazy. Okay, as soon as I get all that done, then I start working on summer schedule, but it's got some time to wait, because you don't need summer until closer to summer. So, so I'm going to you know, move this way for a while, trying to catch up on grading. Okay, the other bit of news, and this was a good news, bad news situation. Next Monday happens to be, you know, oh, what's tomorrow?
Tomorrow is voting.
Yes, it is. You better remember, okay? Yes. I hope you've made a plan and you're going to vote.
I have.
Okay,
I'm
excellent.
scheduled to work, but I'm going to call them and tell them I might be late.
Okay. I've already done the same thing here. I've let people know I might be late getting in because I've got to vote at the beginning of the day because I don't get off until 7:45 and the polls will be closed by then. So I've got to vote on my way in this tomorrow morning. And I don't know how big the crowds will be. I hope it's going to be a big crowd. I hope there's huge turnout in the right direction. Yeah. So anyway, that's, we'll see what happens with that. But then next Monday, this is sort of the good news, bad news situation. Next Monday is Veterans Day observance. Actually not Veterans Day, but when the state observes it. And the two-year college system, that is a state holiday. So that's the good news, but the bad news is we won't meet. Oh, get over it. Okay, yeah. So anyway, we'll move on from there. All right. Now, I was just wrapping up example 5 in your text, which is on page 925. This is in section 13.6, directional derivatives and gradients. We're finding applications of gradients, and that's what example 5 is. It follows that the direction of the maximum increase is the direction of the gradient, okay? So the gradient for this function was, and we just had done this on the previous slide, minus 8xi plus 2yj at the point 2, -3. That would be minus 16i plus 6j. So that is the direction of the maximum increase. That answered the first question. And then the second says the rate of increase, which would be in the direction of the directional derivative, and the directional derivative magnitude would be the gradient. That's not the right way to say it. The maximum value of the directional derivative is that, and that will be the rate of increase in that direction. So that would be the square root of 16 squared plus 6 squared, that's 256 plus 36 is 292. And the square root of 292 is approximately 17.09 degrees per centimeter, which is pretty amazing. You're out here at least between 3 and 4 centimeters from the center, okay? And you know that's the hottest spot by our original formula, because everything is a decrease from the center, and it's only 20 degrees there, and yet this is moving at 17.09, increasing 17.09 degrees per centimeter, and you're still, like I said, more than 3 centimeters out here, but you're already at negative temperatures here. If you plug these values in, 2 times 20 minus 4 times 4, that's 16, that would be 4 right there, minus another 9, that would be -5. So you're -5 degrees Celsius here, and as you make your way up the gradient, you've got to be curving inward because you've got to be going towards the center. Right there, it's not. The direction of the most rapid increase depends on sort of the topography of the rate increase, but ultimately it's got to be pointing toward the center because that's where the hottest point is. Okay. So, and that's exactly what example 6, I think, is going to show, if just glancing at the figure there. So, ready to move off of example 5? Okay. Now, this is, again, an application of the gradient, and that is on the next page. So, let's do example 6. That's not a lot of space to write from. That's not a lot. I think actually the best place to write from is this one, okay? So, a heat-seeking particle is located at the point 2, -3, which we just did, on the metal plate, whose temperature at XY is the very temperature we just did. That's why I wanted to use that, but there's not much white space. the path of the particle as it continually moves in the direction of maximum temperature increase, and let the path be represented by the position vector. So here is your position vector R of t, which is x of t I plus y of t j. Okay. A tangent vector at each point, x of t, y of t, is given by your r prime of t is going to give you your direction of your tangent vector, x prime of t I plus y prime of tj. Okay. Because the particle seeks maximum temperature increase, directions of r prime of t and your gradient of the temperature t are the same at each point on the path. Okay, so your direction r prime, that's the path it's taking, and it's going toward the hottest point, so it's got to be following the same path as your gradient is outlining, you might say. Okay, and your del F from the previous slide, from the previous example, let me write down what your temperature, okay, that's great, your function is. Temperature, function of x and y, is equal to 20 minus 4x squared minus y squared, right? Yeah. So your del t of xy is minus 8xi minus 2yj. Okay. Now, we just said, oh, okay, I thought you said, okay. We just said that because this is the, the direction the particle is doing, if it's seeking the warmest point, that has to be in the same direction of the gradient, because the gradient is the maximum temperature increase. Okay? Now, what that says to you is the minus 8x here has to equal the I direction here, dx dt in the I direction there. Okay? Now, not equal to is proportional to. It could have some constant proportionality. Okay? We can't exclude that. And then your minus 2y is also going to be sub the same constant times dy dt. Okay? This value here. Okay? They're in the same direction, but they don't have to have exactly the same value. The k depends on the time, the little t time. By solving each equation for dt over k, which is a strange way to do it, equating the results, boy, I've never seen a math book write something like that. Oh boy, that is so interesting. So what they're saying here is pretty incredible to read this from a math book. Multiply both sides of the equation by dt. Okay? Alright, that wipes out the dt's over here. You get dt times minus 8 is equal to k dx. Okay, and then what we want to do is divide by k. Okay, I'm sorry, yeah, divide by k. Okay, and then divide both sides by the minus x. So dt over k, strange, is equal to dx over minus 8x. Okay. You do the same for the other one, this one, the y value, and you have minus 2y all right. We want to multiply both sides by I had written this here, so let's do the same thing. Let's multiply first by dt, both sides. So minus 2y dt divided by well, we won't go there yet. All right, almost gotten. Okay. There's our dt. Multiply both sides of our dt. Minus 2y dt is equal to k dy dy. Okay. Divide both sides by k, because that's what we want, dt over k. And then divide both sides, the k's go out here, by a negative 2y here. And that'll be a negative 2y there. And that'll be dt over k is equal to dy over negative 2y. All right. I think I finally got that straight. So, we have that the minus dx over 8x is equal to minus dy over 2y. Now you can wipe out the minus signs. They're both gone. All right. And what you do at this point, and this is, it sort of aggravates me to get into differential equations here. I don't know why they insist on doing something like that, but here's what you do. If you integrate both sides of this, this would give you 1/8. I can't write. Okay. Yuck. Okay. One-eighth log x. I can't get my pen back. Here we go. Well, Now I got it. Okay. Log x is equal to 1/2 log y. Okay. And if you want x as a function of y, and for some reason they're doing x as a function of y rather than y as a function of x. And I don't know particularly why that's the case, but let's do it. Let's multiply both sides by 8. So that would be log x is equal to 4 log y. All right. Double the class size just right there. Okay. How many is here? Okay. Go over because you might not listen to it on YouTube. I kind of did finally finish spring term. I've got just a few little tweaks to do to it, the schedule. So I'm finally able to start attacking some of the grading that I'm way behind in. So, and things aren't in Blackboard yet because I don't have everything graded yet. But I'm going to start working on that today. I've got, like I said, just a little bit of a tweak to do to the spring schedule, but after that, I'm hoping to be grading. Oh, I forgot this other thing. Sometime this week, we also have a faculty meeting, which may throw a wrench into things, but if I'm not mistaken, I don't recall exactly what time, but because I'm in class so stinking much, all 4 days of the week, and it won't be one of these 4 days, the odds of my making the faculty meeting is pretty slim because I'll probably be in class. Usually they have it on Tuesday or Thursday. I believe it's Thursday. And Thursday afternoon I've got a mini-term class and I can't afford for them to miss a class. So we'll see. Okay. But anyway, I hope to be working on grading, except when I'm in meetings or something like that. And then number 2 was this coming Monday is Veterans Day. Are you familiar with that?
Yes.
Okay, and Veterans Day for the state of Alabama, at least the two-year college system, is a state holiday. So the good news is Monday's a holiday, but the bad news is that means we won't be meeting Monday. So get over it, okay? So we do meet Wednesday, but we will not be meeting Monday. Okay, so anyway. All right. What we're doing, this is example 6 at the bottom of page 925. We're dealing with gradients, and this book has a really bizarre way of doing this, which happens to work okay, but it does tend to be a little messy. And you'll have to just go back and listen and see how we got here. But anyway, we got down to the point of 1/8 log x is equal to 1/2 log y. So I'm multiplying both sides by 8, and that gives me log x is equal to 4 times log y. Okay? Now, if you do, the next step here would be log x is equal to log of y to the 4th. Okay? Rule of logarithm, 4 log y is the same as log of y to the 4th power. And then you take the e of both sides and you get x is equal to x is equal to y to the 4th. Okay? Clean that up a little bit. And they introduce some constant c to make that true, because it within a constant of that. Okay? And that gives you your solution to the differential equation, the two differential equations we had there. And then you know the initial point of that, and I didn't write it down here because it's the same one we used before, but the thing started at the position 2, -3. And since 2, -3, you know the point, the particle was at that point. You can plug that into this equation. X equal 2 equals c times the -3 to the 4th power. That would be the 81. Because -3 squared is 9, and 9 times 9 is, okay, that'd be 81. So that means the c is equal to 2/81. Okay? So, plug that back in here, x equal 2/81 y to the 4th. So there is the function of the path that you would be going in. The path of the heat-seeking particle would be x equal 2/81 y to the 4th. And they do show that in the figure. And if you don't have a book, let me show you here. It's the same way it starts, and then it bends and does something like that. Actually coming in tangent to the y-axis, something like that. So there is the path that we just described on the other. We knew this was the initial point from the example 5. We knew it started off going in this direction because that was the direction of the derivative there, the gradient there is the direction of the highest increase. And then it has to, like I said before, curve in to go toward the center. Now what we didn't know was how long it took to do that, whether it was going to be something like this or what. And this comes in, stays within the 3rd quadrant, or 4th quadrant the whole time, and zooms in that way. And perhaps that's how it has to be, otherwise I think you would have been going up or down in temperature at some point. So there's that. And it's not completely obvious to me that that is the function y is equal to 2/81, x equal to 2/81 y 4th, though that could easily be the case. I think it does look that way. All right. Okay. Now, they jump right to example 7. And I kind of hate that because what they have at the top of page 926 is some pretty important verbiage there. Okay? In the figure that I just drew, the path of the particle determined by the gradient at each point appears to be orthogonal to the level curves. Now, let's go back to this figure here. And my drawing isn't the best. I admit that. Okay? But even here, that seems to be at a right angle here. It is. Okay? This one seems to be at a right angle. This seems like, with a little imagination, could be at a right angle. That looks pretty close, and that one almost definitely is at a right angle or awfully close to it there. They should be, because your gradient vector always is crossing the level curves perpendicular, because it's always going up at the highest gradient, the greatest slope. So that's the characteristic there. A little hard to see in my figure, but if you look back at the one in the text, they sure enough do look like they're all crossing perpendicular, and they have to be. They do. Okay. So, this becomes clear when you consider that the temperature is constant along with a given level curve, so the maximum rate of increase would be not that way or that way, that would be 0, 0, so the maximum is somewhere in between. Okay. So the point xy on the curve, the rate of change of t, temperature, in the direction of the unit tangent vector, u, is 0. And All right, I think I'll erase this because we don't need the specific problem anymore. But let me put this in here too now. Again, in fact, I think I'll back off here and write it here. Okay. The rate of change of temperature in the direction of the unit tangent vector u is 0, because the unit tangent vector goes in the direction along a level curve, and of course there is no change of temperature there. So it can't be in the direction of the tangent vector, it's in the direction of the unit normal vector, okay? So the conclusion for this is the gradient vector, now they're going back to F now, we were just using T, xy, dot the unit vector, okay, any unit vector, this is your directional derivative u in the direction of the unit vector. Now they go back to T's. I don't know why they're changing like that. xy, this has to be 0, okay? The dot product of, this needs to be T of xy. I don't know why they went to F, okay? Because the dot product of u and F is 0, you can conclude that they must be orthogonal to each other. And that then is what this theorem is saying. The gradient is normal or perpendicular or orthogonal to the level curves at every intersection of a level curve. The gradient is going in the direction of the maximum increase, so therefore it has to be exactly orthogonal to the level curve, which is 0 increase, okay? So that puts it in that direction. So here's what that says. If f is a differentiable function at some point x0, y0, and the gradient of f, x0, y0, is not 0. Now remember, the gradient is a vector, so this is a 0 vector here. So that's saying you can't have no gradient. You've got to have a gradient that is non-zero. Then the gradient at x of alpha x0, x0, y0 is normal to the level curve through that point x0, y0. Okay? Everyone, all the time. So now I think we're ready for example 7. Finding a normal vector to a level curve. Sounds like a relatively straightforward thing to do. Justin's here. Okay, it's hard to have to stop every time and say this, but just to let people know. Last Friday, I basically almost got the entire spring schedule finished, of my part anyway, which is way late, but there were so many changes to be made, I had to make sure it was all done right. And as far as I can tell, I think I got everything right. But then I happened to think there were a couple things I could do to make it better. So I haven't done that. So this afternoon, I'll probably start on that, okay? I'm hoping it won't take me more than 5 minutes, 15 at the most, but you know, hopefully I will be able to get that done. Of course, I've got to finish eating lunch first. I don't have time between classes to do that. I never have time between classes to do it. But anyway, so tomorrow, so once I get that done, then unless something else comes up, I'm grading papers and grading papers and grading papers, trying to get caught up because I've let these slide while I've been working on the schedule. Okay, so if you don't see anything in Blackboard, that's why. I've got to get these things caught up. Okay, number 2, what's tomorrow? Say again? Voting, election day. Please vote. Are you eligible to vote? No, okay. So please vote if you can, okay? And then the other thing, and this is a little early to tell you this, but just since I don't know if I'm going to see you, you know, any given day, like last week, let's see, it was just, no, two of you came in last week. The first one, it was just Muhammad and me. And then that was on Monday, and then on Wednesday, it was Justin, Muhammad, and me. So I never know when I'm going to see anybody in this class. So I wanted you to know, Monday, I don't know if you're familiar with this, we have, oh yeah, I've already told you, Veterans Day. And on the two-year college system, that's a state holiday, which means, sadly, we don't have class. So get over it. We will not be meeting next Monday. School is closed next Monday, okay? But we will be meeting Wednesday and then the following Wednesday. But school is closed next. Okay. Let's move on. Sketch the level curve corresponding to C equals 0 for the function given by f of xy is equal to y minus sine x. Okay. And find a normal vector at several points on the curve. Say again? Oh, okay. So, how are we going to find a normal vector of that curve? Where will that be? Where will you find the normal vector? Help me. What is the title of this section? Directional derivatives and, look at the top of your book, gradients. So let's take the gradient. Let's do del f, and gradient is a vector, that's why I put the arrow over it, at xy, okay, is equal to what? F sub x I plus f sub y j. What's the partial of this f with respect to x? Say again? Not y. If you're taking the partial of this function with respect to x, this has no x in it. So you try that as a constant, partial of that is 0. And what would that be? Negative cosine x. Right? Derivative of sine is cosine. No. Derivative of cosine is negative sine. Derivative of sine is positive cosine. The derivative of negative sine is negative cosine. Okay. I don't know if this is helpful to you or not, but this is how I remember. The sine function goes like that through 0, doesn't it? Okay? Derivative of that is 1. Isn't that what cosine is? 1. Okay? So, same direction. Whereas derivative of cosine here is 0, and sure enough, sine is 0 there, but cosine's derivative is negative here, but sine derivative is positive there, so derivative of cosine is negative sine, derivative of sine is cosine. I don't know if that's helpful or not, probably not, but that's one way to think of it. Okay, think of their slopes. So derivative of this with respect to x is negative cosine x in the I direction, and then plus j. 1 is the partial of f with respect to y is just 1, right there, 1 plus 0, okay? So there is your gradient of f, and that would be the direction of the normal vector, okay? Now, says sketch the level curve corresponding to c is equal to 0 for the function that. So I think all they mean by that is just set f equals 0, okay? So 0 is equal to y minus sine x, so that is y is equal to sine x. Now this seems way too simple, but what that's saying is this is your normal curve, where this is your, that is your function y is equal to sine x. So that's a level curve corresponding to c is equal to 0. In other words, your f is 0, okay? Now, find a normal vector at several points on the curve. Well, let's pick the point here. What's the normal vector there? At 0, 0, this would be minus 1 I plus j. I don't know that I can find the normal vector at several points. That would be the point 0, 0. Here at this point, which would be pi halves 1, that would be 0, 1. So the normal vector here would be minus 1 minus ij, so it would be down that way, and that is normal, okay? Up here it would be I just did it, but I didn't write it down. At pi halves, this would be 0, 1. So that would be in that direction. So you see, they are normal to that curve everywhere on the curve. Okay, let's see if that's what, yep. Okay. Oh, I'm sorry. I was finding the level curve. That is a level curve. And then find a normal vector at several points on that curve. Okay. At the origin, it'd be minus, I'm sorry, I drew it in the wrong direction. Minus 1j would be in that direction. And then at 0 minus j, that would be 0j, that would be in this direction. Okay, sorry, not here, okay? And then at, over here, that would be at pi 0, and then plug that in here, and you'd be at negative 1, 1. Negative 1 I, that would be in that direction. Nope, they point it in the other way. Oh! Oh, negative cosine, yeah, I'm sorry. It's negative cosine. Cosine of pi would be a negative 1, but negative, that would be a positive 1 I. So that's in that direction. So you see, at every point there, you would have a normal, a perpendicular vector. And that's what they mean. They drew more in the book. You're certainly welcome to look at all those that you want to. Okay. All right. That was example 7. Oh, here they do it. I forgot. Wait. All right. Goodness gracious. All right. Let's see how they proceed. The level curve for c is equal to 0 is given by 0. That's, you set the c c equals 0. The alpha of xy equals 0 is equal to this. And that would just be y is equal to sine x. And then this would be a curve from the xy plane following the sine curve along the x-axis there. And this would be a cylinder, an open cylinder that follows that sine curve. Okay? So those are the values forever. Okay? Now, that's the level curve. That's the first thing. Find the normal vector at several points. Well, the normal vector would be the gradient at any of those points, and that would be f sub xy, f sub x at xy I plus f sub y at xy j. That would be minus cosine xi plus j, always plus j. You can use theorem 1312 to conclude that the del f, the gradient of f, is normal to the level curve at every point xy. So just pick a few points. I would have started 0, 0. They will put 0, 0. That would be minus 1, 1. Okay. So 0, 0 minus an I plus 1 in j, so it would be up this way. Okay. And sure enough, that's perpendicular to that sine curve there. They went over to minus pi. Yo, at minus pi, cosine is negative 1, but minus cosine would be a positive 1, so it's 1, 1. So this would be in that direction. And sure enough, the curve comes like this, and that would be in that direction. At pi halves 1, that would be the next point on that curve, pi halves 1. At pi halves, cosine of pi halves is 0, so it would be 0, 1. That would be going straight up. So just like we said, every one of those would have a value that way. So del f at, wow, they picked a really weird point, negative 2/3 pi, which would then have a value of negative root 3 over 2, and that would be at, goodness gracious, 1/2 I plus j. Weird value, okay? Now, where that came from is cosine of this, okay? Cosine of negative 2/3 pi. That's over in the third quadrant, so that's a negative value, and it's 1/2, but negative of that would be a positive 1/2, so there's 1/2 j, I plus j. So it would be 1/2 in the I direction, but 1 in the j direction. So it would be something like that. So you keep on going at negative 1/2, negative 1. Because when, I wish they showed the whole thing on the screen at once, but they don't. There is y is equal to sine x, okay? Y minus sine x is 0, okay? So when x is equal to minus pi halves, y is equal to minus 1, okay? So there's your minus 1 there. And then you plug in this, the del f at that place is going to be cosine of minus pi halves. Cosine of minus pi halves is 0. So it's going to be 0 plus 1. And there's just j. So there's, and that just goes straight up then. So, and they just picked several more and just throw in some more at the end. And let's see, please finish with these so we can show. There's the graph. Okay. So in all these, it's always plus j, so j is always pointed up. The j component is. If there's an I component in the -1 direction, J is that way. -1/2 direction would be there. 0 direction would be there. +1/2 would be there. No, -1, okay. And so that always the J component is upward, and the X component varies. Like these. Okay. Sometimes negative, sometimes positive. Okay. And that would be gradient vectors, the direction of maximum increase. There's example 7. Now we move to functions of 3 variables. All right. Now I hope you realize, oh wait, I didn't bring in my watch. I thought I always brought it in. I guess I left it on my desk. How are we doing on time? Second? 1 minute to go. We're not going to get too far on this, but let's just hit functions of 3 variables. Directional, can't even read that in a minute. So that's where we'll start next time. Okay? The definition for directional derivatives and the gradient can be extended naturally to function 3 or more variables. As often happens, some of the geometric interpretation is lost because you don't have any dimensions to talk about. So you cannot interpret the directional derivative of a function of 3 variables as representing a slope that you don't have enough dimensions. So we'll start with there next time. And there's just one more example, and then we're through with the section. So here's homework exercises here. Do either 3 or 5 or both. They're both at Calc Chat. 3's at Calc View. Do either 7 or 9. They're both at Calc Chat. 7's at Calc View. Do either 11 or 13. They're both at Calc Chat. Either 15 or any of the odds 15 to 19. They're all at Calc Chat. 17's at Calc View. Do either 21 or 23 or both. They're both at Calc Chat. Do either 25 or 27. They're both at Calc Chat. 25's at Calc View. Do any of the odds 29 through 37. They're all at Calc Chat. 31's at Calc View. Do either 39 or 41. They're both at Calc Chat. 41's at Calc View. Do either 43 or 45. They're both at Calc Chat. And then do any of the odds 47 to 55, I guess it is. They're all should be at Calc Chat. Then do 57, it's both at Calc Chat and Calc View. 59 is both at Calc Chat and Calc View. There's a true-false here. You can do either 61 or 63. They should both be at Calc Chat. I don't see any examples here with 3 dimensions. So it looks like you can do them all. 67 should be at Calc Chat. I thought for sure there'd be at least one or a set that would have 3 dimensions, but they don't have any that I could see. Maybe I missed them. Do any of them except 3 or more dimensions. All right. So we'll pick up from there and go next time doing 3 variables, and then we'll move on to 13.7. Okay? And once we finish 13.7, there's 13.8, okay? And let's see. I think we may stop after 13.8. Lagrange multipliers we're not required to do, so it just gets a little too involved in 13.9 is applications of extrema, but I think we'll get enough of those with 13.8. So I'll try to, after we finish 13.8, have your test ready for you for chapter 13. All right. Good deal. All right.